The next speaker is Stephen Chuang from University of Akron. He received his diploma from Taipei Institute of Technology and his PhD at the University of Pittsburgh in 1985. He joined University of Akron in 1986, where his research interests are C1 chemistry, hydroformylation, NO-CO reaction, and acid catalysis. Thank you.
Okay, how we know how to use this?
Just press this.
Okay.
Thank you.
Well, it's my great pleasure to come here to discuss with you about my research. First of all, I'd like to acknowledge my graduate students, which 3 months to perform this experimental work. I also had to point out here the research I have here do not have immediate commercial interest. And again, here we are interested in how the reaction occurs rather than to find out the immediate application of this. Rhodium has been a major component. Rhodium is a major component in the automobile catalytic converters. And the major function of rhodium is to catalyze the reaction of carbon monoxide with NO to form the nitrogen and carbon dioxide. And the mechanism of this reaction has been proposed by Professor Belt and a couple of investigators. And here is a proposed mechanism. The first step is involved with the absorption of NO and absorption of CO to form adsorbed species. And this adsorbed NO can dissociate to form the adsorbed nitrogen and adsorbed oxygen, and the absorbed oxygen can react with adsorbed CO to form carbon dioxide. And these adsorbed N species can also react with NO, adsorbed NO to form N2O or N2 species. And CO has proposed at temperature below 553, the dissociation of NO may be a rate determined steps, and at temperature above 553, the recombination of N2 may be a rate determined steps. While rhodium is a very expensive metal, so we understanding of how this rhodium catalyzed reaction catalyzes NO-CO reaction may help us to develop a knowledge for improve how the rhodium catalyzes reactions. Assume is CO can absorb on the rhodium surface in various form pairs, and this can form the linear CO, rich CO, gem dicarbonates, or if rhodium is oxidized, it can also form the linears on the rhodium plus sides here. And if we add the cesium as a promoters, it's been proposed this cesium can bend the CO down to form the TLC-CO. And it would be interesting to find out how this adsorbed CO interact with the NO to lead to the formation of CO2 and N2. And the NO can also adsorb on the surface of rhodium to form the cationic NO species, and the neutral NO, or this anionic NO species, and these are NO nitro species. And all these NO species exhibit a different vibration frequencies. So infrared spectroscopy is an ideal technique to study these NO-CO interactions. So the objective of this study is to investigate the interaction between the adsorbed NO and the CO species, and examine the effect of cesium on these adsorbed species, and also how this cesium affect the resonance time of the intermediate leading to the CO2. And we also like to use the infrared technique to study the role of NCO during the formation of CO2. The catalyst we use for this study is a 5% rhodium silicates. And this silicates, and the reason we use high rhodium here is because high rhodium can provide linear, when CO adsorb on the high rhodiums, which give the linear and bridge COs. Most of the commercial rhodium catalytic converters use around 0.5 or 0.2% of rhodium in the catalytic converters. And here we use the high weight percent loading here. And this loading, we also have been using this loading to do the CO hydrogenation and high alcohol synthesis. And cesium was added by, and this catalyst was prepared by the impregnation techniques. And we have used a post-CO chemistry to characterize this catalyst. The infrared cell we use for this study consists of 4 pieces of flange here, with a cooling water jacket to cool the O-ring so that we can conduct a reaction here at high temperatures. And this hollow stainless steel cylinder here is used to separate the catalyst from the calcium fluoride windows in the side here. And in order to observe the primary adsorbed species, we have filled this empty space here with a calcium fluoride rod, so that we can primarily see the adsorbed species instead of the gas phase species. And this reactor can be operated up to 450 degrees C and pressure up to the 60 atmosphere. But in this study, we only conduct the reaction up to the 1 atmosphere. And the effluent of the reactors will be analyzed by mass spectrometers and the gas chromatographers. And there's various lines and valve here was designed so that was put together so we can conduct a post-CO chemistry, temperature program reaction, temperature program desorption, and steady-state reaction and isotropic transient study. The first set of results I'd like to show you here is how the anodes interact with the adsorbed COs. Okay, we have conducted 2 experiments here. The first one is how the gas phase anode interact with the adsorbed CO and how the gas phase CO interact with the adsorbed anode. But here I will only report this part of result. Okay, the first set of data here is how the anode interact with the adsorbed COs on the loading silicon catalyst at 100 degree K. We have conducted at room temperature. The result at room temperature is very similar to the result at 100 degree C here. Let's take a look at this data here. The first thing we do here is to adsorb CO on the loading catalyst. And adsorbed CO gives a band at 2048 weight number and 1900. This 2048 is assigned to the linear CO. This 1900 is assigned to a bridge CO band. And then we pass around 25 microliter of the anode through this adsorbed species. And as you can see, when the anode passing through, the linear COs react, intensity of linear CO band decrease. And there is a slightly change in the bridge CO band. As we continue to pass anode through, we can see the linear CO drop and these loading anode plus bands start to form. And then we put a lot of the anode in. And this large amount of anode essentially depress all the linear and bridge CO out of the surface. And the mass spectroscopy analysis of gas phase product found there is no CO2 formed during this process. So most of the linear CO was in fact just dissolved. And then anode adsorbed on the surface as anode plus and anode minus. The same study was conducted on the cesium loading catalyst. Okay, before we pass the anode through, we can dissolve CO on the surface of catalyst. In this case, we see the linear CO here, a bridge CO, and a band at 1766 here, which has been assigned as a TLD CO species. Then we pass the anode through. As we pass the anode through, and again we see the linear CO drop more rapidly. Intensity of the linear CO decrease more rapidly than the intensity of bridge CO and TLD CO. And then as this linear CO drop, the loading anode minus forms. And again, then we put a large amount of anode into the system. We can see the linear CO and bridge CO and all of this TLD CO was displaced. And mass spectroscopy analysis indicate all these adsorbed CO simply dissolve to the gas phase. So essentially, there is no reaction occur at 100 degree K between the gas phase CO, gas phase anode with adsorbed CO. So the next experiment we conduct is a post-transient study. In this case, what we do here is we pass a steady state flow of NO and CO through a catalyst. Then thirdly, we use a gas sampling bar to introduce 10 cc of the C13O into the systems. And this 10 cc of C13O will replace another 10 cc of C12Os. And we use a mass spectroscopy to observe how the product is formed. And this reaction was conducted in an infrared cell, so we can see how these adsorbed species interact during this switch. So here is the mass spectroscopy result here. As we can see here, here is a C13O pulse indicated by this square. And then we have this regular C12O. Regular C12O is indicated by this solid line here. So the symmetric shape of this pulse here indicate C12O was replaced by C13O at a 1-to-1 ratio. So essentially the surface was not disturbed. And we can see here CO2 also is produced under these conditions. CO2 is formed following the C13O2 is following the C13O. And residence time of this intermediate lead into this CO2 can be determined by integration of these response curves. So this result here indicates the CO and the NO can react at 100° K, but when we put the CO on the surface, but the adsorbed CO cannot directly react with NO, so it requires presence of gas phase CO to promote the reactions. And here is an infrared spectroscopy of adsorbed NO and adsorbed CO during the pulse study. And the infrared spectrum here is very complicated, but what I want to show you here is the spectrum we think here is different from what we have seen earlier. So this clearly indicates the surface state under the NO-CO flow is entirely different from the surface state when we expose the adsorbed CO to NOs. So let me quickly summarize our observation here. The linear CO dissolves more readily than the bridge CO when adsorbed CO is exposed to NO. And we also have conducted interaction between the adsorbed NO with the gas phase CO species. And what we found is NO plus is more readily dissolved than NO minus and other nitrite and nitrate species. And exposure of these loading catalysts, exposure of these loading catalysts to NO and CO lead to the formation of CO2. So presence of gas phase CO is important to lead to the formation of CO2 here. And the presence of cesium on the catalyst inhibit the formation of IHNCO, and presence of cesium also increase the amount of CO desorptions, and also increase the tau CO2 to decrease the tau CO. Tau represents the residence time of the adsorbed species. The next experiment we conduct is a temperature program reactions. And the way we conduct this experiment here is after we conduct a steady state NO-CO reaction, we decrease the temperature down to room temperature, then slowly heat this catalyst at 10° K per minute up to 400° C or 673° K here. The 28, mass 28 here is this is the mass of the nitrogens, and this is the mass of the NO, and 44 is the mass of the CO2 and N2O species, and 46 is the mass of NO2. So as you can see, the reaction there's a slow, there's a little bit of reactions at a low temperature range, and the extensive reaction occurs at the 530° K, and the near complete conversion of NO is occur at 573° K. And let's take a look at the infrared spectrum here. In the low temperature range, the dominant adsorbed species are NO species. there is very little CO adsorbed species observed. And as the temperature increase up to 453 degrees K, we start to see the rhodium gem dicarbonyl species. And as the temperature increases up to the 553 K, the major species on the surface is RHNO and SiNO species. And there's also a small amount of linear CO sit on the surface. Essentially, all the NO species is being converted and is rapidly converted to the product, and we do not see the NO adsorbed bands. Okay, the same study was conducted on the cesium rhodium catalyst. What cesium did here is decrease the temperature for the complete conversion of the NO to the N2 and these NO2 species. So here I'd like to quickly summarize my observation here. The cesium decreased the temperature for the nearly complete conversion of NO species, and cesium reduced the spillover of NCO from the RHNO to the SiNCO species. I do not show you the infrared result because the limitation of the time here. Okay, the last set of results I'd like to show you is a steady-state isotropic transient study. In this case, what we do here is to use the step transient techniques to investigate how these adsorbed species interact. And here is the result here. This study was conducted at 523 degrees K. The reason we select this temperature is based on the TPR result. As you can see in the TPR result, the significant reactions start to occur at 530 degrees K. So we decide to start the reaction at this point here so we can see the adsorbed species during the reactions. So let's take a look at this transient result here. Okay, the way we conduct this experiment is here. Again, we pass the NO and CO flow through the reactors at a ratio of 1:1 at 523 K and with 1 atmosphere. And at the reference time 0 here, we switch the C12O to C13O. It's a step change. So C12O drop very rapidly down to 0, and C13O is increased to the up to 1. This is a normalized response. As FT curve, normalized step response here. C naught indicate the initial concentrations. C infinity indicate the final concentrations. And argon is coming with the C12O here. So argon response can be used to estimate the effect of transportation line on the transient response of CO2. And this dot here is inverted argon response. Okay, basically this is an artificial, it's not a true response, but we just take an argon curve and reverse it in the other ways here. So from this result here, the integrations of the area above the response curve is equivalent to the average residence time or intermediate leading to the CO2. Let's take a look at this case here. For the case of CO2 is a dotted line. CO2 response come out slightly earlier than CO. So this result indicates the reaction leading to CO2 is faster than the desorption of CO. And we have conducted the same study on the cesium rhodium catalyst here. And what the cesium did here is cesium decreased the residence time of the intermediate leading to CO2, and also decrease the residence time for the adsorbed CO. And here is the infrared spectroscopy of the reaction of this transient during the step transients. Initially, we have there should be a plus sign here. We have RH plus. Rhodium gem dicarbonyls. These carbonyls are in the C12. This is a C12 rhodium gem dicarbonyl species, and as you can see, during the step transient, this C12O is being replaced by C13O species, and adsorbed NO species remain the same because the system was not disturbed. And let's take a look at the several band here. The first one I want you to point to you is this NCO band stay with NCO band absorbed on silica, and this band remain the same during the step transient here, and so this remain the same here. This is indicative of the species which is spectator species which does not involve in the reaction. And there is another band I want to show you here is RHNO species. This RHNO species also switch with the GM dicarbonia species, but it switches at much slower rate. And we have plotted intensity versus time and compare with the gas phase response. So this is a band. This is a 2130 band. 2130 band response. And this 2130 band is corresponding to the RHNO species. And so these RHNO species switch at a much slower rate than the gas phase product. So this result here indicate this RHNO NCO species is also a spectator species, does not directly involve in the formation of CO2. So this result basically confirm what Professor suggested 10 years ago. Okay, this is my last slide. Basically what I like to do here is to conclude our observations. At low temperature, at 100 degree K, 100 degree C, linear CO dissolve more readily than the bridge CO species when the adsorbed CO is exposed to the gas phase NO. And NO plus dissolve more readily than the NO minus and the nitrate species when the adsorbed NO species is exposed to CO. And exposure of these loading catalysts to the NO and CO will lead to the formation of CO2 at the same temperatures. So these results here indicate the presence of CO is important to promote the reactions. And at this moment, I do not have an explanation for that. At a higher temperature, around 523, both SNICO and RHNCO species are spectator during the CO2 formation. And at higher temperature, 573 degree K, this is equivalent to the 300 degree C, RHNCO and SNICO are the dominant species. And cesium effect has been identified that cesium decreased the residence time of intermediate leading to CO2 at high temperature. At a temperature above 523 K. And cesium also reduced the temperature for completely NO convergence. And cesium also decreased the spillover of NCO to the front loading to the silica surface. Thank you.
We have time for questions.
Van Ice, Penn State. Stephen, I was wondering on the role of the cesium. Chemically, why does it have its effect? If you look at the chemistry on the surface, why is it having that effect on the CO and the nitrogen species? Do you know?
Based on the literature, the cesium is supposed to provide a site for the oxygen storage. Okay, so in our result here, we've shown the residence time of intermediate leading to the CO2 is much smaller on the cesium formaldehyde catalyst. So maybe there's a oxygen available on the cesium side to interact with the CO to form the CO2. So at this moment, we still need to do the labeling of the O in order to identify the proposal. So what we do here is on C13O only. Yeah. So that's a very that's a part of the research we are going to conduct in the near future. So at this moment, we can only interpret our result based on the C13O transients.
Troy from Yuguang. Well, you mentioned that there's a reported that there's a lot of report about the cerium the
Yes.
role of the helium. And
Yes.
one of them, as you mentioned, it is the oxygen storage.
Yes.
And well, in the assignment of the CO on the helium doped
Yes.
catalyst, you said that around 1700 is assigned for some kind of tilted CO.
That's right,
on
yes.
But is that possible to assign it as a instead of the tilted CO, just a threefold CO? I didn't tell that probably two of them bridges to that rhodium, and that the other one probably helium, something like that. And the other question is that if it is that usually at the 1700 wave number, means that the bond energy between the rhodium and the CO is increasing, okay, which seems to me increase at the resonance time. I mean that harder to be reacted. Of course, it depends on the existence of the other reactors, because it is a little bit contradictory in that reason. So can you explain about it?
Yes. Whether that band at 700 is a TLD CO or three-bonded CO there's no conclusive evidence, but there's an analogy between the organometallic chemistry and the CO adsorbent surface suggests the band could be a TLD CO species. And that TLD CO species, according to our observation, does not play any role in the catalysis at high temperature. Because at high temperature, the surface is not in a reduced state. And that TLD CO is only present when the surface is in a reduced state. So at a high temperature condition, when there's a presence of NO and CO, TLD CO is not present. So there is no contradictions, because that TLD CO is only present when the rhodium catalyst was completely reduced, or that CO is only present when the catalyst is exposed to COH2 or in the reducing atmospheres. In the oxidizing atmospheres, the TLD CO is not present. And I have shown that too. We do not see a TLD CO when the catalyst is exposed to NO and CO. Yeah, so that some of the literature result try to use the TLD CO to explain the cesium catalyst more active. Okay, that's the wrong assumption, because under the NO-CO atmospheres, there is no TLD CO at all.
So actually, that tilted CO is not related to any activity at all.
That's right. Yeah.
Well, let's thank the speaker for an excellent presentation.
The next and last speaker for this morning session is Professor Jae-Sung Lee from Chuang University of Science and Technology. I think you are familiar with the Chuang Institute of Science and Technology, but we are in the process of changing names. So I'm saying Chuang University of Science and Technology.